joining us for the IEEE Computer Society Standards webinar series, brought to you by the Standards Activities Board. With over 225 standards that transform the way we live, work, and communicate, the IEEE Computer Society sets the standard for design automation, simulation, testing technologies, Ethernet and Wi-Fi, quality assurance processes, systems architecture, DevOps, and more. Standards deliver best practice processes for developing market-ready interoperating systems, products, and services. You can have an impact by joining one of the over 200 IEEE Computer Society Standards working groups. Participating in one of the working groups grants you access to information that reduces risks, increases proficiency, and shapes the future of the industry. Help determine what's next in computing technology. Learn more about our standard working groups at computer.org/standards.
Okay, so hello everyone. Thank you for joining us today and welcome to today's webinar from our Standards Activity Board series and today's presentation from the IEEE 802.11 working group. My name is Edward O, and I am the Vice President for Standard Activities of the IEEE Computer Society. Before we get started, I would like to address some housekeeping items. This webinar is being recorded. You can ask any questions in the Q&A box you see on your screen. The speaker will answer as many questions as possible after the end of his presentation. When submitting a question, please reference the slide. A copy of the slides and the recorded webinar will be emailed to you tentatively tomorrow. Circling back to today's presentation, Wi-Fi is important to all of us. The IEEE 802.11 working group, which is managed by our Computer Society Layman Standard Committee, focuses on developing these cutting-edge, high-quality market-relevant standards for wireless local area networks. Actually, you may hear lots of useful and practical applications about IEEE 802.11, especially on Wi-Fi 5, Wi-Fi 6, and now Wi-Fi 7, which is the focus of our webinar today. In this webinar, we are very happy that we have our speaker, Dr. Alfred Estarajudi, about this topic for discussion. Alfred is currently a system engineer in wireless R&D at Qualcomm Technologies Incorporated. At Qualcomm, Alfred focuses on the design, performance evaluation, and standardization of medium access control protocols for wireless systems, with a special emphasis on increasing efficiency, scalability, and reducing power consumption in wireless networks. Alfred currently serves as chair of the IEEE 802.11be, also known as Wi-Fi 8. He is also currently the chair of IEEE 802.11be, also known as Wi-Fi 7, and he previously served as vice chair of IEEE 802.11ax, that is Wi-Fi 6. He also was the editor and vice chair of the Wi-Fi IEEE 802.11ah for Wi-Fi Halo. He made significant technical contributions to different IEEE 802.11 amendments in both standardization and certification of Wi-Fi interoperability. Alfred received his PhD degree in information engineering and a bachelor and master degrees in telecommunications engineering, all from University of Padova in Italy. Lastly, before we welcome Alfred and give the floor to him, as a last reminder, please note that as per the IEEE Standard Association Standard Board Operation Manual, at webinars here, any individual presenting information on IEEE standards shall make it clear that their views should be considered as their personal views rather than the formal position, explanation, or interpretation of the IEEE. Now I will give the floor to Alfred to start the presentation. Hey, Alfred, good morning. Thank you so much for accepting our invitation and present the latest status of the Wi-Fi 7, especially what it has been done under your leadership. Thank you, Alfred. You now have the floor.
Yeah. Thanks, Edward, for having me. And thanks everybody for welcoming me to give this presentation. So yeah, we'll focus on 802.11be on this particular webinar. And so we'll start with a quick outlook of the Wi-Fi industry. So we have had a tremendous growth in Wi-Fi over the past 20 plus years. As many of you know, we started in 802.11 around 1997. And since then, we have had billions of Wi-Fi devices shipped over all over the world. And essentially, we addressed connectivity in a lot of retail enterprises, venues, and many more other use cases are being addressed as we move on. So the trends over the years have been expanded to include multiple bands. So we have addressed 2.45, 6 gigahertz. This was most recently. We have had the developments also in the sub 1 gigahertz and the 60 gigahertz bands. And the targets are essentially to increase the throughput, focusing on peak throughput using MU-MIMO technologies, and increasing the network throughput in dense deployments. And that can be thought one of the use cases of 11ax, which was Wi-Fi 6. And a better coverage. We have different technologies that are already developed and under development to address mesh networks, outdoor coverages, and so on. Other trends, of course, is improvements in latency and reliability, which is essentially the focus of also the Wi-Fi 8 technology that is under the works right now. And since at least a year, all Wi-Fi related technologies have been migrating to WPA3 to enhance security. And we're also addressing, from an 802.11 perspective, new applications which are beyond communications, which is kind of our bread and butter, but focusing also on positioning, RF sensing, wake-up radios, which are other amendments that have been developed or are under development in 802.11. So thinking from the mainstream perspective, so mainstream is essentially using the 2.45 and most recently the 6 gigahertz bands. So if you think of it from 802.11 and Wi-Fi Alliance synergies, usually we develop standards in 802.11, and these standards are taken as a basis from Wi-Fi Alliance certification to release products that all of us use on our daily basis. And this kind of provides, this slide provides a kind of a snapshot of how these new technologies are brought into the market. So starting from 2008, we had Wi-Fi 4, which was based on 802.11n, and we are moving towards, in 2012 to 2015, we moved to Wi-Fi 5, which was based on 11ac, and then Wi-Fi 6, which is essentially products are still being on the shelves, and then, which is going to be the focus of today's presentation, Wi-Fi 7, which is being terminated as we speak, so in 2024. And the next essentially trend is going to be covered under the 802.11be and ultra high reliability umbrella. So Wi-Fi 7, which is based on 802.11be, is going to be the focus of this presentation. And when we defined the PAR, the scope was essentially to enable a mode that supports a maximum throughput of at least 30 gigabits per second. And that was a check. Enable a mode that improves the worst case latency. And of course, as per our tradition, we always strive to ensure that every standard that is developed is backwards compatible with devices that are operating in those bands of operation. So the timeline for TGBE is essentially shown here. So we are kind of at the end of our project. So we recently received the EC conditional approval to move the draft to RevCom, which is expected to happen in September 2024. And once that is concluded, then the draft is going to be considered published and will be incorporated in the 802.11 main draft. So a quick summary of the features of 802.11be is I'll use interchangeably EHT and 11be, where EHT stands for extremely high throughput, and it's an acronym that we use to identify the stations that follow 802.11be devices standard. So we have included several features, and this is not an inclusive list of everything that has been defined in EHT, but these are the kind of the main features that were defined. So we expanded the bandwidth to cover 320 megahertz so that we have gains in terms of peak rate and rate versus range gains. The introduction of a 4K QAM. Prior to 11B, we were limited to up to 1K, and this brought around 20% of peak throughput improvements. Multiple RU aggregation preamble puncturing, essentially to improve spectrum utilization, and several enhancements from in the 6 GHz band once FCC clearly defined the rules of operation in the 6 GHz. So to ensure that we have range improvements to overcome the PSD limits that were defined from a regulatory perspective. And moving to the MAC layer, so we enabled multi-link operation where you operate over multiple links, while traditionally we operate over only one link. And this was done to improve latency and also provide throughput gains for in the bands of interest. Several features were also introduced to ensure that we reduce the latency. These were essentially to overcome channel access latencies and add to the predictability of gaining access to the medium via essentially sharing quality of service parameters between the devices, a defined mode, which is called restricted target wait time, to ensure that the time at which the station accesses the medium is protected, and some kind of reverse direction protection of the transmissions in the uplink with trigger single user scheduling, and also a feature which is for emergency preparedness communication services, and we will cover this a little bit more in detail later. So as per traditional, so we start with the PHY layer of EHT, and this is going to cover the main improvements that were brought to the PHY from 11BE. So as I mentioned, so we added support for the 320 megahertz bandwidth. So moving from 160 to 320, it gives an obvious double peak throughput, and also it improves the rate versus range at high PHY data rates. For example, and this improvement is due to linear bandwidth versus log SNR trade-offs. You can see in the right figure where you have the more than 50% range improvement for many of the arrays that are available from a standards perspective. We did also support for the 4K QAM, which achieves 10 bits per second per hertz per spatial stream with 5/6 LTPC codes. So overall, it accounts for around 20% in gain from a throughput perspective. Overall, the peak PHY throughput is essentially increased on a per link basis to more than 23 gigabits per second, accounting for an 8 spatial stream communicating device. So from a generalization perspective, if you think of it, the 11B was built on top of 11AX, so that is our starting point, and as such we inherited the bands and the bandwidths that are supported by 11AX devices. So 11AX also supported 2.4, 5, and 6 gigahertz bands. So we inherited 20, 40, 80, 160 megahertz bandwidths of operation, and we added the 320 megahertz channelization. So currently we have 3 non-overlapping 320 megahertz channels, and others are overlapping partially for a total of 6 channels in the 6 gigahertz band. So by means of puncturing, essentially by playing with the transmission of the PPDUs over the 320 megahertz, we can also obtain other bandwidths of operation. For example, you can still achieve a 240 megahertz transmission in a punctured mode by either puncturing the first or the fourth 80 megahertz subchannel. There are also other puncturing patterns that are available, which are essentially used to mitigate interference from incumbents, for example, or other BSSs operating in the area. So we can provide static puncturing that the AP advertises to the stations in the beacons, and these punctures are not expected to change frequently during the lifetime of the BSS. For example, if you think of a subset of channels that are being used by an incumbent, we can suppress transmissions on those particular channels to avoid interference. We also have the possibility of dynamic puncturing, where the PHY header of the PPDUs themselves contain a map of which of the subchannels are not containing any transmission, essentially, so that you can puncture the transmissions on the fly. This is a subject, of course, to the static puncturing as well. So you perform dynamic puncturing on top of the static punctures that the access point is already providing to the stations. So the other feature that had significant enhancements from a PHY perspective is the resource unit in an OFDMA design, where we added the possibility of multiple resource units aggregation. So essentially a particular station can send its data not only in one resource unit allocated to it, but it can actually have more than one RU allocated to the station, so that if you use it together with preamble puncturing, you can improve the scheduling flexibility and improve the interference management. Because this way, for example, if you see in the bottom right figure, as a station, you can puncture a particular subchannel, and you can allocate 2 RUs for the lower leftmost part transmission and the rightmost part transmission, and still be able to essentially retain most of the spectrum that is available for your transmission while not causing interference to incumbents or radars or other BSSs that are operating in the area. So the other part that was being refined while we were defining 11BE was that FCC finalized the rules for power operation in the 6 GHz band. So there were a definition of 3 different AP power classes. So we had standards power, lower power indoor, and very low power. Each of them with their own rules in terms of operation from an access point. So, for example, standard power it still is subject to automated frequency control, and a third-party entity that is managing the enablement of the operation in that particular channel. Low power indoor is essentially you can only deploy these access points and their stations indoors. And a very low power, which is the default case where there is limitations in minus 5 dBm megahertz maximum transmit power and 14 dBm total, whichever of course is lower. So given that these rules had a limit which was on the power spectral density, we defined several modes to increase the range that is incurring due to the PSD limits. And those methods were based essentially on duplication of the transmissions over multiple channels. For example, the generation of PPDUs with beacons that are duplicated over multiple 20 megahertz increases the likelihood of the reception of this beacon on a wider range due to replication of the information. And we also defined EHT PPDUs that were also duplicated, and they additionally had a dual carrier modulation for essentially providing some gains due to repetitive encoding with different modulation mapping. And of course, you have a 2x gain due to the RU duplication as well. So this was done to essentially improve the range in the 6 GHz band when PSD limits were in place. So the preamble structure, and generally in mainstream amendments, so when we define also new PHY modes, we also define new PHY preambles. And in EHT, we kept backward compatibility, of course, with Wi-Fi 6 and prior to it. We also introduced a new PHY preamble that is based on the universal SIG that is expected to be present also in future amendments as well, so that it improves forward compatibility. And of course, given that we continue using the legacy SIG field, this is going to be preserving the backward compatibility that I mentioned earlier as well. And looking from a forward perspective, there is several information that we keep in the in the universal SIG, which is going to be decoded by future amendments, that contains, for example, the version identifiers that you identify whether it's 11BE, for example, or 11BN and so on, the bandwidth of the PPDU, so that when you detect the PPDU over the air, you know for what bandwidth that PPDU is occupying, and a certain other information as uplink, downlink flag, TX obturation, BSS color that are beneficial from a MAC perspective. So another part that was that came in EHT is essentially unification of the PPDU type. In 11AX, we had different types of PPDUs. So we had HE, MU PPDU, SU PPDU, and extended range PPDUs, which kind of complicates parsing from a receiver's perspective and the generation from a transmitter side. So the group decided to have a unified PPDU type for both SU and MU transmissions. And these are essentially the transmissions that the station sends while performing EDCA. And one type which is unavoidable for the trigger-based PPDU, since these PPDUs do not need EHT 6, given that the access point is providing the transmit parameters to the station. And essentially, it added also the flexibility that each EHT SIG portions in the 80 megahertz, they can also contain different contents, which is traditionally not the case in the .11, because we want the stations to always decode in the 20 megahertz, in the primary 20 megahertz. Here, this was done to essentially ensure a little bit of reduction in signaling overhead for the case of multi-user transmissions, where the EHT SIGs contain transmit parameters, and on the receiver side, the receive parameters for decoding the different resource units that are allocated to these stations. So moving to MAC, so one of the kind of the signature feature, if you will, for 11B was multi-link operation, essentially enablement of transmitting frames over multiple links. And to enable that mode, so the group defined an entity which is called a multi-link device. And this entity has multiple affiliated stations, which are the traditional stations that we use in 11AX and prior to it. And it has also an additional higher layer MAC data service and a single MSAP that connects to the logical link control, so that all the data that is being transmitted on these different links is essentially collected by this MAC-SAP and provided to the LLC, to the higher layers. So the benefits of multi-link operation are essentially increased peak throughput, because you can have multiple packets of the same traffic flow that can be sent over multiple links. So if you have a link that is congested, the other links are likely not going to be congested. So you can essentially transmit those packets on the other links as well. And of course, this also improves the latency. And we also have the flexibility of performing some traffic steering. So essentially, we can partition different traffic types to different links to aid low latency traffic. So think of if you want to dedicate one link to voice traffic and another link to best effort, we have the tools to do that. And also, it brings improvements from a power save perspective. So, of course, the more links you have, the more power you need to save, because you have multiple RX front ends, multiple the MAC PHY layers that are essentially enabled, that are consuming power. So when we define multi-link operation, we made sure that not all of them need to be on at all times. So you can simply monitor with a single radio and wake up the other radios on demand. So essentially only when, for example, traffic is needed to be delivered or received, you can essentially wake up the other radios. So from a high layer perspective, so the MLD contains essentially two functionalities from one upper portion and the lower portion. So the upper MAC is essentially common at the MLD level, and this is essentially handling the interfacing to the higher layers, starting from the LLC and above. So we have a single MAC SAP interface. We have one single MLD MAC address that identifies the device to the higher layers as well, and which can essentially be a new MAC address, or it can use one of the MAC address of one of the affiliated stations. Anything that is related to sequence number maintenance, block scoreboards that are being used to essentially track the receive status of packets and so on, they are kept at the upper MAC so that the entity determines whether the frames are being received correctly, whether there is any duplications that need to be dropped and so on. And of course, security is handled also at the upper MAC to ensure that, that all packets that are being received are decrypted and validated in an unambiguous manner. We additionally added some enhancements to better handle higher rates that are that came due to the PHY enhancement that we discussed, and also due to the increase of number of links. So up to 11AX, we had up to 256 block bitmaps in block sessions. So we added 512 and 1K block bitmaps to improve the to increase the number of MPDUs that can be aggregated within the same PPDU, so that you do not have a limitation on the PPDU lengths that you can transmit over the air due to the aggregation limits that we had earlier. And we did require also mandatory support for GCMP encryption as opposed to CCMP that was traditionally the case prior to 11BE. Lower MAC PHY are separate, so at the station level, so thinking of the devices in the 2.4 gigahertz or in the 5 gigahertz, they are going to autonomously handle any link-specific functions. So think of channel access, sounding, power save functionalities, synchronization, scheduling, maintenance. They are all handled separately and independently by the stations. And of course, each station is identified by their own MAC addresses. So as I mentioned, security is at the MLD level. So we have a single association and security context, so essentially one password, if you will, per multi-link device. And authentication is performed over a single link. However, when you perform association and authentication, you also are able to set up operation over multiple links. And these are performed via four-way handshake mechanisms that are relying as much as possible on existing protocols, for example, association requests and responses. So we maintain a single pairwise transient key for exchanging frames and encrypting frames that are exchanged between the two peer MLD entities. And they are essentially generated by using the MLD MAC address to ensure uniqueness. Similar consideration from a packet number perspective for individual address frame, we have a single packet number which is handled at the MLD level. And these PNs are essentially checked to ensure that there is no replay attacks on the incoming MPDUs. And similar functionalities are handled also from the AAD perspective. When you construct the AAD, you use the MLD MAC address so that you avoid encryption every time that you transmit the same, you retransmit one frame from one link to the other. Having said that, group address delivery is has preserved legacy behavior, so it's on a per link basis. And that is because these APs that are affiliated with this MLD are also serving legacy stations. And the legacy stations do not understand what an MLD device is. So they expect their keys, so group temporal keys, to be untouched and unchanged. So that beacons, management frames that are being sent on each link, they are using their own independent keys. And this is essentially inherited from 11AX and other legacy amendments. So delving a little bit more in the details from a multi-link perspective, so we have expanded all the basic functionalities of a MAC protocol, if you will. So starting from the discovery, so passive discovery is essentially preserved. We use beacons, probe responses, and these beacons and probe responses that are sent by an AP. They do additionally carry partial information of the MLD, so that stations that are members of, that are affiliated with an MLD can use this information to early understand whether an AP is a member of an AP MLD, so that it can perform multi-link setup as soon as possible. And given that this information is often partial in the passive scanning phase, so we do have an active scanning phase, which is based on probing. And during this phase, the non-AP MLD can additionally probe the any of the APs that are affiliated with an AP MLD to gather the complete multi-link information for that AP MLD. This includes, of course, capability-related parameters and also the modes of operation of that AP on that particular time. And once you have all this information, of course, you can do multi-link setup. So you essentially associate, authenticate, and set up the number of links that you want to use during your association with that access point MLD. Post multi-link setup, we have also the possibility of reconfiguration. So say that for a specific amount of time you want to use 3 links, and then at a given time you want to reduce that number of links to say 1. You can reconfigure that operation. So essentially you can request the AP to reduce the links that are dedicated to your communications to 1, and you can also update certain parameters for that particular operation. So you can essentially update MLD related parameters and capabilities so that you do not need to use the same resources that you were using when you were operating as a 3-link MLD device. Configuration modes. So from a multi-link perspective, they differ whether you are an AP or a station. So from an AP perspective, in general, APs are more complex devices as opposed to non-AP stations, which are supposed to be simpler because an AP is supposed to handle multiple stations communicating with it and also offload the traffic to the higher layers. So we do have 2 modes for an AP. So we have multi-link, multi-radio, simultaneous transmit receive. So essentially an AP MLD is capable of receiving and transmitting at the same time independently over multiple links and process this information technically independently between the stations and forward it to the higher layers. We do have a mode which is, if you will, a little bit simpler from an AP perspective, which is multi-link, multi-radio with non-simultaneous transmit receive. This is was intended to address the case of a mobile AP. And this has limitations in terms of not being able to transmit and receive at the same time due to internal constraints. For example, due to poor RF filters, frequency separation between links would cause inter-AP interference, if you will. So there are a lot of rules set in place that ensure that the transmissions of, towards this AP or from this AP MLD are starting at the same time and are ending at the same time so that they do not cause interference between the links. From a non-AP MLD perspective, keeping in mind that from a non-AP perspective, we have a power save always as one of the KPIs that we need to make sure that we do not cause an increase in terms of power consumption. So we have several modes, multi-link single radio. So essentially a station can hop from one link to the other. And essentially you have only one device, one radio operating at a given time. It does bring flexibility as you're moving across links. So if you see that one link is busy, then you can transition to another link and try your luck essentially on that other link to transmit your packets. Enhanced multi-link single radio is an enhancement to the MLSR mode where the station is additionally capable of simultaneously listening on multiple links. And this benefits from link diversity because the stations listen over multiple links and the AP is the one probing the station on any of these available links to make sure that the station receives on that particular link. And if the station does receive in that particular link, then the station can turn on the full radio to exchange frames with the AP. Multi-link, multi-radio, as the word says, so it's a multi-radio device that is capable of simultaneous transmitting over multiple links. And we have 2 subcases, whether the station is a simultaneous transmit receive capable or non-simultaneous transmit receive capable. And of course, this brings benefits from a multi-link aggregation perspective. EMLMR is a subcase of the multi-link multi-radio where device has the additional flexibility of dynamically reconfiguring spatial multiplexing capabilities on each of the links while operating. So the next slides kind of give an overview of how this multi-link single radio, eMLSR, and MLMR operate, but kind of goes along the train of thought that I just explained. So multi-link single radio, the station is jumping from one link to the other, and in order to make sure that the AP knows that the station is jumping from one link to the other, it uses existing power-safe protocols to tell the AP in which link it is actually operating by essentially declaring to be an awake state on one link at a given time. Enhanced multi-link single radio has, due to the capability of being able to listen on a set of links at any given time, to simplify and to benefit from the legacy perspective. So we make sure that the MLD that is operating in the MLSR can receive certain frames in when it is in listen mode. These certain frames are MURTS trigger or BSRP trigger that are very simple from a PPDU perspective. So they are required to be sent in non-HT PPDU, so legacy PPDU with a mandatory rate of up to 24 megabits per second, so that the RX front end in listen modes can be as simple as possible. So it just has to receive this specific initial control frame. And once one of the stations in this eMLSR links responds to the initial control frame, then the eMLSR MLD can turn on the full radio to continue the frame exchanges. And of course, given that the main radio needs to transition from one link to the other, depending on where the initial control frame is subsequently going to be sent, there is a transition delay or link switch delay, if you will, where the station where the AP needs to take into account that the station may need some time to essentially go back into a mode where it can receive another initial control frame. Multi-link, multi-radio. As I mentioned, there are two modes: simultaneous transmit and receive, and non-simultaneous transmit receive, depending on whether you have a TX-RX isolation. So if the bands are very near, for example, if you have two links in the 6 gigahertz band, then you likely are going to have cross-channel interference, for which you may not be able to handle. The only way that you can handle it is by essentially making sure that the PPDUs are being transmitted start and end at the same time, so that also your transmissions in response are starting and ending at the same time. So the NSTR mode allows this alignment of the PPDUs to ensure that there is no interference caused to the other links due to the transmissions of the companion link, if you will. As I briefly mentioned earlier, so we do have the possibility of traffic steering. So with the TID to link mapping, we can map certain TIDs, which are traffic identifiers. So think of, for example, if you want to steer voice from one link to the other, depending on the channel conditions of that particular link. So you can essentially perform this traffic steering to make sure that the traffic with the highest priority is served at the earliest, as opposed to best effort, where you might not have the same requirements. And also from an access point perspective, it kind of helps also in load balance. So if you have high data rates that are being used for a particular stream, you can offload that particular stream in a wideband link, for example. And of course, it manages coexistence, because you may have other legacy devices operating in that channel, and if that channel is being used for high data rates, then it will add to the latency of all those legacies. So additional features. So quickly focusing on the low latency perspective. So to essentially help an access point make this determinations in terms of what traffic is going to be prioritized with respect to other traffic. So we rely on legacy mechanisms such as stream classification services to classify incoming MSDUs. MSDUs are essentially the frames that are coming from the higher layers. And once you classify these MSDUs based on the parameters that the non-AP stations are providing, then you can essentially start providing scheduling information at the AP side to better serve this particular stream. For example, we add a QoS characteristics element in this negotiation phase to indicate, for example, the minimum data rate that is being expected by the station, whether there is any delay bounds, burst sizes, and so on, that can additionally help the access point to make the correct determination from a scheduling perspective. Next to the restricted target wait time, essentially the goal of the protocol is to ensure that all transmissions of the AP has this service periods negotiated with the station, for example, station 1. And in order to make sure that that start time is protected so that either the AP or the station 1 gains access to the medium as soon as possible at that expected start time, the requirement is that other stations that support this feature that are transmitting prior to that start time, they are required to end their TXOP at or prior to that start time of the TXOP, so that the channel is likely idle when the access point or the station 1 is accessing. In addition to that, the protocol also allows the station to indicate to the access point which of the traffic flows that it has deserves higher priority with respect to others. The other mode of operation that helps from a latency perspective is trigger TXOP sharing. So the access point aids the stations to, so the access point gains access to the medium. And that particular TXOP that is obtained by the access point can be used by the station to send uplink data to the access point or to another peer device. And hence we have two modes of operation, one which is only for uplink, so data to the access point during the TXOP, or uplink or peer-to-peer. So you can also help protecting frames that you're sending to another peer device that need necessarily not be within the same BSS as your own AP. Last but not least, emergency preparedness communication service was introduced to provide prioritized connectivity to authorized users. So think of when the networks are congested due to disaster or emergencies, so floods and earthquakes. So this feature allows certain MLDs to negotiate higher priority contention compared to other devices that are operating in the area. That way, for example, firefighters have a better channel access than other members that are in the area, so that they can use the internet with a better reliability as opposed to the viewer that is taking videos and so on. So yeah, in terms of conclusion, so 11b introduced a lot of new features. Some of them are 320 megahertz 4K QAM, MRU aggregation, puncturing, MLO, low latency enhancements. And the goal was essentially to achieve higher throughput, higher reliability, and lower latency, and while preserving the very important backwards compatibility with legacy devices. So I think that's it.
Okay, thank you very much for your great overview of the latest standard development related to Wi-Fi 7, Alfred. Perhaps let us have a Q&A to answer a couple of questions before we conclude, Alfred. So actually, Alfred, if possible, perhaps you go back to the slide related to MLO, because there are quite a number of questions on MLO. So the first question I can see from the Q&A box is that, does the multi-links have to support WPA3 only?
It's mandatory required. And that is actually a requirement from a Wi-Fi Alliance perspective. To the best of my recollection, in 802.11, we do not exclude other protocol suites, if you will. But we do have a requirement of supporting WPA3 from a practical perspective, if you will.
Okay, great. Sure another question related to security is, can the MLO be configured and used in open security?
So that's a question which is kind of beyond the standards. So I'm not very familiar with open security, but I don't think it's defined in 802.11. But if it is, then we rely on all 802.11 related security suites that we have there.
Okay, great. And then another question from the audience about the MLD is that from his point of view, he is asking, is the MLD in 802.11be something similar to the VGPP carrier aggregation?
I'm not very familiar with carrier aggregation in 3GPP, but if I see it as carrier aggregation, and I would kind of think that carrier aggregation is kind of more similar to multiple RU aggregation that we have. But yeah, I have limited knowledge on that particular functionality of 3GPP.
Okay, no problem. We can talk it offline also. So then we have a few questions relate to physical layer. The first one is more on the higher bandwidth because you mentioned that in Wi-Fi 7 we now have 320 megahertz bandwidth. So the question is that from the audience is that usually higher data rates have lower range. For 320 megahertz is higher data range, data rate. How does it have better range?
Oh yeah, so let me go. So that is by the replicate, the repetition that we discussed briefly. And let me find that slide.
Yeah.
So we have this mode which is called the HT duplicate PPDU. We transmit a duplicated PSDU that is duplicated over, for example, 80 megahertz, and we use the dual carrier modulation to add additional repetitive gains. And that is essentially overcoming the PSD limits that we have from that perspective.
Okay, awesome. And then another question is more about the puncturing. So the question is that when puncturing gets modified, does the station need to reassociate again? Is CSA required?
No, so essentially when I'm assuming it's being discussed about static puncturing. So the beacons contain this punctured bitmaps that the stations receive every time that they receive the beacon. We do have this classified as a critical update so that if a station is sleeping and it misses the change in static puncture, there is a critical update indication in the beacons that indicate, okay, go wake up, read for example, DTIM beacons, which are mandatory required to be read for receiving this critical update of parameters. And that actually can be done either via beacon parsing. You obtain the EHT operation element that contains the puncture modes patterns, or by the CSA mechanism that was mentioned by the commenter as well.
Okay, great. Actually, there are quite a number of more questions back to MLO. So, because Alpha, you can see from question 10. So, one question is how many links are possible to have for the MLO configuration? I think it's more critical implementation.
Yeah, so there are up to 16 links. I do believe that one of the links is considered reserved. So, theoretically speaking, you can have up to 15 links for an MLD. But in practice, you will have to consider that you have limited amount of channels in the 2.4, 5, and 6.
Okay, cool. And then another question is because you can multi-user OFDMA and MLO work coexistent? I think his question is rather the multi-user OFDMA and MLO can be used together.
Yeah, the answer is yes. So MUFDMA is a link level functionality. And so as an MLO, you're independently using all the features of the links and providing aggregation benefits by using the link diversity. So yes, you can use MUFDMA and MLO at the same time.
Okay. And the question 12 may be a little bit more complicated to explain, but let's just try. But Alfred, if see if you want to answer a lot. The participant want to know more about the EMLSR. I mean the enhanced multi-link single radio. So his question is rather the enhanced multi-link single radio has any additional frame exchange?
Yeah, it's a bit of a tricky question. So the only differing property that I can classify is that this initial control frame and the response frame that is being sent, you can think of it as an additional frame exchange that essentially turns on the main radio. But that has multiple benefits, because not only it tells the station to turn on the full radio, but it also protects the medium due to NAV setting properties of this initial control frame, control response frame. So the if you think of it, the only added part is the padding that you would need to essentially turn on the full radio, and that is essentially being provided as a MAC padding in the trigger frame itself.
Okay, great. Another question about MLO. So people want to know more about the MLO. So during the multi-link operation, in which link it is expected to receive more data, either 2.4 gigahertz band, 5 gigahertz band, or 6 gigahertz band, or in general, is there any way to do configuration on this?
Yeah, so from a standards perspective, essentially it's kind of beyond the standards, but experience-wise speaking, so your scheduler has to take into account not only the available bandwidth that you have in that particular channel, but also the range that you can achieve, because the higher you go in the band, the lower the range that you can achieve, and also the channel utilization and the particular parameterization that the stations are using. Because, for example, 2.4, you can only operate in 20 megahertz. 5, you can operate up to 160. 6 gigahertz, you can also operate in 160. 6 gigahertz is freer. 5 gigahertz is less free. 2.4 is busy. So, there is a lot of things to consider in channel selection.
Okay, great. Let's do the last question. So question 7, because we missed it. So actually the audience asked, I'm not sure how, that this referred to, either it's 11BE or MLO, but his question is, how does this work with IPv6?
Oh yeah, that's transparent to 802.11. Yeah. It's a higher layer. So we are transparent from above LLC. So whatever comes via MSDU, we transfer that information to the next peer, and that is being transferred as is. So whether it's IPv6 or IPv4, there is no difference from an 802.11 perspective.
Okay, it's awesome. Thank you so much, Alfred. And actually, for those who join me, I keep seeing questions about, can we get the presentations live? Definitely, as long as you are registered. So we will send you the slides and the recorded webinars in the next 24 to 48 hours. So once again, I would like to express my sincere thanks to Alfred for joining us today and sharing what is going on in the world of the 802.11, especially on the latest development on the Wi-Fi 7 under his leadership. So another thing that I would like to point to you is that it is a quick programming notes. Actually, intermediately after the end of this webinar at about 9 a.m. Pacific time or the 12 p.m. Eastern time, our computer society will have the 2024 presidential candidates town hall that you can also use the link here that to join, so you can hear from our president candidates about their perspective if they are elected as the president, and they can answer any of your questions during the town hall meeting. So once again, I would like to thank Albert and our society staff for supporting us and joining us today, and for all of you for attending and for a lively Q&A discussion. Thank you again, and have a great rest of your day. And Albert, thank you so much again. We appreciate your effort. Thank you so much. So the event is now concluded. Thank you so much. Have a great rest of your day.